Hello everyone, today we're talking about transformation of functions, section 2.5 in our book. So, suppose the graph of f is given. They want us to describe how the graph can be obtained from the original graph of f. So they're going to give us like a base function such as f of x equals x cubed, and then you'll see the type of transformations that occur to the graph. So in this video, I'm going to give you a whole lot of examples that include graphs. But I wouldn't copy down necessarily every single graph. Maybe copy down the actual word definition of what is happening. I'm giving you the graph to give you a visual representation. But by all means, do whatever works best for you. But this one will have a whole lot of examples, so it'll take up a lot of space if you try to copy every example. But as always, do whatever works for you. So here we can see our basic graph of f of x equals x cubed. So this is the graph that I'm going to use to give all different examples of all the transformations happening to the f of x equals x cubed graph. The first, it gives us f of x minus 2. So it's telling you if f of x is x cubed, I'm moving down 2 units. So if the subtraction is outside of my function, it just means I'm moving down 2 units. So here we can see the basic example of x cubed. Here it has been moved down, shifted down 2 units. So if it asks what happens to the graph of f of x when y equals f of x minus 2, all you need to simply say is it moves down 2 units. Okay, likewise, if the plus 3 is outside of our function, it's going to move up 3 units. So here again, our basic x cubed, right, and it has moved up 3 units. So it's shifted up 3 units. Now we can see that x plus 3 is in our function. We're actually substituting x plus 3 into our function. So when we have x plus 3 being substituted, this plus 3 is counterintuitive. Right? So if it's actually in the function, it's like backwards. So instead of moving right like you might think the positive would, this x plus 3 actually causes the graph to shift left 3 units. So here we can see the basic one, and then we've taken our graph and shifted it 3 units to the left. So a plus inside of our function causes it to go left. And then obviously a minus inside of our function is going to cause it to go right. So our original function, here we can see it shifted 4 units to the right. So when it's inside our function, x minus 4 means we're moving it 4 units to the right. If I have a 3 times my whole function, right, so I'm vertically stretched by a factor of 3 if the 3 is being multiplied by the entire function. What that vertical stretch means is, here I can see that my x cubed function goes through the point 1, 1. Here, when I have my 3 times x cubed, my 3 times my function, we can see that the y is already at 3 by the time x gets to 1. So it's going up 3 times quicker. We call that a vertical stretch. Okay, so if it's a number outside of our function being multiplied by our function, and it's a whole number, it's a vertical stretch. So, the opposite of that, if we have a fraction times our function, we call that a vertical shrink. And it's a vertical shrink by a factor of 1/3 in this case. So again, we have our original function, x cubed. We can see that when x equals 2, y equals 9 here. But over here, we can see that when x equals 2, y only equals 3. So it's a shrunk by a factor of 3. Right? It's going up much slower now, in this case by a factor of 3. The other one was going up much quicker. We call it a stretch. This one, a shrink. Vertical shrink. And that's, again, when it's on the outside of our function. Okay, let's say we want y equals negative f of x. So we're going to negate the whole function. When we negate the whole function, it reflects over the x-axis. So here we can see we have the point -1, -1. right? And when we put negative f of x or negative x cubed, that becomes negative 1, 1, right? We flip that over the x-axis. So all of our points will be flipped over the x-axis here when the negative is outside of our function. When the negative is inside of our function, when we want to take f of a negative x, it's going to cause a reflection over the y-axis. So here we can see the point 1, 1. It's been reflected over the y-axis. Now it's at negative 1, 1. And you'll see that negative f of x and f of negative x actually produce the same result, but we can see how it would also flip over the y-axis. So this graph just happens to have symmetry with both. But if it's inside our function, reflection over the y-axis. Next, if we have 4 times x being plugged into our function, so this is different than if it were 4 times f of x. Since this is f of 4x, we're multiplying x by 4. We call this a horizontal shrink. So this is horizontal shrink. It's very similar. You can see it's pretty similar to a vertical stretch. But if it's on the inside, it's a horizontal shrink. And it's by a factor of 4. In this case, we can see that with our x cubed function, we go through the point 1, 1. Whereas my f of 4x cubed, when x equals 1, y already equals 64. Because I had to cube that 4. So they call this a horizontal shrink because we're bringing the graph in, right? We're shrinking the graph, going up much quicker. Then, opposite that, a horizontal stretch. If we have a fraction times our x inside of the function, we call that a horizontal stretch because we're going to stretch out the graph. So here on x cubed, we can see that we have the point 1, 1 again. And it took us all the way out to 4, 1, to well, x equals 4 to get up to the point y equals 1. So horizontal stretch, we've stretched our graph way out. Okay, so that's the difference between verticals or a horizontal shrink and a horizontal stretch. Horizontal shrink goes up quick. Horizontal stretch, very spread out. Takes a long time to get to the same altitude. Okay, so that's it with transformations of our graph. So go back through, review whatever you need to figure out what translation does what to each graph. And again, we'll have practice on that tomorrow. And the second part of our section determines if a graph is even or odd. So to determine if a graph is even, you plug a negative x.
Dismiss.
So to determine if the function is even, I plug in a negative x wherever I see an x. And if my function looks exactly like it did originally, it's even. So if it didn't change any of the signs, if it looks exactly the same, it's even. To determine if the function is odd, I do the same, I plug in a negative x. But if it is the negative of my function, right, so if all of the signs have changed, then it is odd. And here I'll show you a couple examples. First example, so to determine if it's even or odd, I take f of negative x, and I plug that in wherever I see an x. So that's negative x to the 6th minus 2 times negative x squared. Well, negative x to the 6th, anything with an even power, right? Squared, 4th, 6th, doesn't matter if the number is negative, it's always going to be a positive, so that's still going to look like x to the 6th. Right? That negative x isn't going to change positive or negative value of that term. Likewise, a squared, right? A negative x squared, that's going to look the same as 2x squared. So we can see that my function, after I substituted a negative x, looks exactly like my original function. So this one is even. It's exactly the same after I plugged in a negative x. Next one, determine if it's even or odd. So again, I plug in a negative x. I get negative x cubed plus negative x squared. And a negative x cubed. negative x cubed gives me negative x cubed, right? Because a negative x to any odd degree, so whether it be 1, 5, 7, it's always going to give us a negative value. So negative x cubed is the same as negative x cubed. So it is going to change that sign. Okay, however, this one is squared. So our negative x will stay a positive x after it's squared. So here we can see that the only sign that changed was the first term, right? This is now a negative x cubed, but this is still an x squared. So I did not change all my signs, so this is neither. So if I don't change all of the signs or none of the signs, it's neither. It's neither odd or even. And now let's do one more example. Again, plug in negative x wherever I see an x. Okay, like I said before, negative x to an odd exponent, that's going to be the same as negative x to the fifth. Right, so that's going to change that sign from the original. And then here I have a 3 times a negative x. So we all know that's going to be negative 3x. So I changed my first term sign, that was a positive, now it's a negative. And I changed my second term sign. It was a positive, now it's a negative. So this is odd, right? So this equals negative f of x. So it's odd. Okay, so go ahead, try the example problems on the PowerPoint. A couple of the questions ask you to graph. You do not necessarily have to graph them. Just explain in words what the transformations would do to the original graph. And once you read the examples, you should understand what I'm asking. And then, like always, we'll go over the notes tomorrow, beginning of class.